Hello everyone, my name is Daniel Medeiros from the University of Glasgow, and I'm here to present our paper about passive haptics and perception manipulation in constrained spaces. So, people are using VR in their daily lives, going instead of more controlled environments, they are using VR in places that are less controlled, like their home, that the virtual environment that needs to adapt to it. So, their home or their office or even in public spaces. One interesting use is in passenger environments since people really pass a lot of time in these environments. But one of the problem is that they have very limited space, so these constraints need to be addressed or reappropriated to improve the way people interact with XR. One way people use VR to improve the way people interact is by using passive haptic surface, such as walls or even stimulating people's muscles to really feel that they're touching their virtual object. But in the one good thing about this constrained environment is you have surfaces all around you, so you basically can calibrate virtual objects on top of these surfaces that you basically make people feel that you're touching really a virtual object, but you're really touching a physical object. So you have a lot of surfaces such as horizontal surfaces such as tray tables or even seat bags are present in most of different environments. But also you have to take into account the social context. So these different surfaces have a lot of different things that they need to be addressed. So one of the problems is that the passive hat improves the feeling of presence, but surface may be located in uncomfortable positions for head and hands and needs to be addressed. So we basically did ask did a study to ask two different questions. So, how the surface type, in case passive haptic surfaces, impacts performance and user preferences in VR, and also how the surface orientation impacts performance and user preferences. So, in our user study, we had two levels. One was surface type, where you had passive haptics, and two forms of different mid-air surfaces with snap, where people can kind of go through a surface, and without snap, the people can go through a surface, and also orientations such as horizontal and vertical. So we had real um, plane seats where we basically had cardboard to hide the indentation so people feel that more like a planar surface, which so basically like a tray table and a seat back. The test that we chose was modified fits law task, where you had basically two subtasks. One is the reaching task, where they reach for a sphere that was calibrated um, according to the center of the plane, where they basically had to reach for this and then reach for the surface. This was one of the subtasks, and the next one, where they needed to drag between task and the surface. So we used quantitative metrics such as throughput, with a task for metric for performance, a path length, time, precision, and we separated these between the 3D component, which is the reaching, and the 2D component, which is the dragging. Also, we collected some user preferences through questionnaires such as satisfaction, task workload, visual comfort, arm exertion, embodiment, which is how people feel connected to the virtual environment. And also, we conducted semi-structured interview for more granular data. So, regarding the results, we found that the passive haptics significantly reduced reaching and dragging times and had the highest throughput and the shortest path length, and also improved people's sense of embodiment. In terms of mid-air, we found that the mid-air with snap increased precision according to the other one, but they had a negative effect on embodiment, especially the self location, because they had to do exaggerated movements to take the hands out of the surface, for example. And the mid air also had overall more fatigue due to the lack of surface to rest the arm. And in terms of surface orientation, we had less definitive results. For example, the vertical had shorter time, but were less precise. But when we ask people about that in the qualitative interview, people preferred the horizontal due to familiarity because it kind of looks more like a tablet, and they felt that it was more on their space. They also said it was little bit less fatiguing for my hand, but in a long-term use, it led to more neck fatigue. So users preferred a vertical for long-term fatigue. Like in the case of these, we found that we need to one way to overcome these type of problems is to use perception manipulation to try and render these objects in a more comfortable ways, not just for the hand but also for the neck. One way is to use perception manipulation, which is done by manipulating what the person is seeing in virtual reality while they do a different action in real life. One way is to use haptic retargeting, for example, where the environment is rotated, so the user feels that they're touching multiple cues, but in the end they're just reaching for one single cube. Another one is the redirected walking, where people it's actually seem as they're walking in circles in real life, but they're really walking in a straight path. And normally these cases are imperceptual manipulations, but in our case, due to the limitation in the space of the environment, we have to use perception and manipulation to alter the virtual space in a perceptible way to increase both comfort and also social acceptability. So we devised a second user study to remap users' movement and also the virtual environment movement to be rendered in more comfortable positions for both the arms and the neck. So for example, for the vertical surfaces, we employed for translational remapping to remap the user's movement and the virtual environment to be in a more comfortable position for both the arms and the neck. And in the case of horizontal surfaces, we use translational plus rotational remapping to render them in more comfortable positions for the arm and the neck. So in the horizontal spaces remapping, you use four different ones where we rotated the surface and the person's movements to basically like to less extreme rotations and also like accordingly to the position accordingly to the eyes of the person. So do from 45, 60, 75, and 90 degrees. And we added baselines for this. And here we show a video of the different ones. So with the vertical remapping, we see that the person is looking straight ahead while reaching for a surface. The horizontal 45, where you have the rotated 45 degrees, and the person is in between the person's head and the surface. 6 degrees, which is a similar one. 75. Again, this is a more extreme one. And finally, 90 degrees. And we see that in this case, they're doing a vertical movement, but their movements are mapped in a vertical way. We use also like the same type of metrics, but included an extra one, neck fatigue. And our results, we found that remapped conditions performed better than baseline conditions, both vertical and horizontal. And also less extreme remappings. The 45 and 60 were preferred due to the trade-off between workload, comfort, and improved precision compared to baselines. And also notice an increased workload on more extreme rotations, the horizontal 75 and 90, and also decreased embodiment scores. We now also notice an increased workload on the vertical remap condition due to the close mismatch between real and virtual movements. So people actually try to match where their hands were. So based on that, we devised 3 guidelines based on the use of perception manipulation and passive haptics. So the first one is to appropriate nearby physical surfaces. The second one is use moderate perception remapping to maintain performance and improve comfort. And when remapping vertical surfaces, consider the proximity of real and virtual hands. And for more information, please read the full paper. And thank you.